All right, so last day we finished convolution, did more examples on convolution. If I have time today, I think I might do one more example at the end of the class. We also started talking about Fourier series last day. So I started showing you why we care about complex exponentials, why they're great, because complex exponential into a system that's linear and time invariant will produce the same Fourier, the same complex exponential. So complex exponential with some frequency going into an LTI system, the response will be the same one, but the scale in front will be different. Okay, so that's why complex exponentials are great. So we're gonna express signals in terms of complex exponentials. So we're gonna try to take a complex and break it up into smaller, simpler pieces. That's something I've been talking about since day one. So the whole goal is, how do we take a signal and break it up into easier pieces? Well, the solution is, or the way we do that is use complex exponentials. So I claim that we can take a signal and break it up into a linear combination, could be infinite or finite, combination of complex exponentials. Okay, and that's what Fourier series will do. It'll give us an equation that we solve to be able to find essentially these coefficient changes. The complex exponential going in and going out is the same, but we need to know which frequencies of complex exponentials we need and what the magnitude scale or the number, that scale in front is going to be. How do we linearly combine them? So this Fourier series equation will be able to will show us how to solve and get that. And then by doing that, we'll be able to express any signal as a linear combination of complex exponentials. And then we can find the response of a system by finding the response of these complex exponentials separately. Okay? I know, it doesn't sound that exciting this early in the morning, but it has a lot of implications. It's good stuff, okay? And it's not difficult to do. All we have to solve is an integral. Okay? So like I've said before, it's a complex math course. Why we're doing that integral is what signals is. Okay? Actually solving it is pretty much basic calculus. All right? Maybe not high school calculus, but stuff you've seen in first year. So a very important thing before we get started, the book approaches Fourier series with a different pathway than I do. What they do first is they do something called the trigonometric Fourier series, which is a complete waste of time in my opinion. Okay? We are not going to do it that way. We are going to do the exponential Fourier series. We're going to solve everything using the exponential Fourier series. And then once we do all that, I'll show you in 2 minutes how the way the book does it, or the first part, the trigonometric Fourier series, is just really a special case of the complex exponential Fourier series. Like they're building it up to the general case, and there's no need for that. We're going to go straight to complex exponential. So anything that homework we have assigned and all that, our expectation is that you do it using the complex exponential Fourier series, which is nothing different really. It's just a general case. Okay, so I'm going to make a note of that. Okay, so I don't believe in this doing this baby step. It's a waste of time. Okay, sines and coses or trigonometric are just complex exponentials in reality. So we're going to go straight to the exponential method of doing that. Okay, and we're not going to, and I'll show you later on, literally in 1 minute, how you can get that trigonometric answer from the exponential answer. Okay, it's really quite easy. So start with some pictures here. So if you remember last day, come on, I showed you a picture at the end of class. I'm going to put it up again. Okay, the prism is probably one of the best ways to picture what we're going to be doing here. Okay, the Fourier series integral is essentially a prism. Okay? So think of the Fourier series integral like a prism. So this is where our signal is going to come in. Okay? And it's going to, the integral, okay, is going to break it up into the Fourier series coefficients. These will be the number in front of a complex exponential. These things. It's going to give us that to tell us how much of each frequency is going to exist in this signal to break it up. Okay, this is what a Fourier series does. It takes a signal and breaks it up in these complex exponentials, a linear combination. Okay, and you got to find these coefficients in front. Another way to think about that, again using pictures. Money always works, right? We always just think about, let's say you have $100, okay? How many fives are in 100? How many tens are in 100 and things like that? So we're trying to figure out how much of smaller components exist within the larger makeup of something, okay? So once we take something like that, or we pass it through that prism, or we do this analogy of money like I talk about, okay, we get a number in front of a certain frequency of complex exponential. So it tells us how much of that specific frequency of that complex exponential exists in this signal. So what we're able to do then is to map or graph in the frequency domain. We call it the frequency domain because we're going to say, for this frequency we have this strong a signal. For this frequency we have this strong. And in this frequency component this much. This one there's 0. So we enter what's known as, instead of the time domain, we can map the frequency components of these complex exponentials, like how much of each of these complex exponentials exists in the signal. So we'll be able to enter what's known as a frequency domain, and then by doing that we can actually plot those values. So for example, in this case, if you say 100 is made up of 25s, 100 is made of 10 tens, and so on, you can take that and you can enter what's known as the frequency domain. Here I'm going to call it the money domain. Okay, and you plot how much of each thing is found inside that larger component. Okay? Another analogy, again, pictures tend to work well with these things. Come on. Another one is, think about this. Let's say you have a smoothie, okay, or an alcoholic drink, for example, okay? And imagine pouring that through something that filters the components out, the ingredients. Okay, so you have a smoothie made up of banana, orange, milk, water, okay? Imagine pouring that through some kind of system that will filter these flavors out. Okay? So you have a banana filter, an orange filter, milk filter, water filter, and then it tells you how much of each one was used. 1 ounce of banana, 2 ounces of orange, 3 ounces of milk, 3 ounces of water. Okay? That's another way of thinking of what this Fourier integral is doing. It's going to take our signal that's composed of all these components, and it'll filter out and tell you there's this much of this frequency, there's this much of this frequency, this much of this one, and this much of that one. Okay? This is what the Fourier integral will do. Okay? This is essentially breaking down a very complex or difficult or larger signal into the smaller components and telling you that these components are this and this and this. Okay? And when you add them all up together, you get your product. Okay? So, for example, in a smoothie, you have the recipe, you know how much of each ingredient is required, put it all together, and you get the result. Or, this much scotch, this much, grenadine, whatever, add it all up, and this is the drink you have. Okay? Yeah, it's simplistic, but that's essentially what we're doing here. Okay? So when we're talking signals now, okay, keep that idea in your mind. So we're talking signals though. We're not talking alcohol and we're not talking banana smoothies. Okay? What we want to find out now is we want to break up a signal x of t in terms of complex exponentials. Okay? So what you're essentially saying is how much of this complex exponential with this specific frequency, omega naught, okay? How much of that is contained in my signal x of t? So how do you do that? You take x of t divided by that. If I told you how many 5s are in $100, you take 100 divided by 5, you say there's 20. So I take x of t divided by that, and then I find how much is in there. X of t e to the minus j omega naught t. Okay, just from that analogy makes sense. Then I want to know, all right, what about the next frequency? What about 2 omega naught? How much of 2 omega naught t is inside that signal? Take x of t divided by e to the j omega naught t. That's what I get. And then the next frequency, 3 omega naught, and 4 omega naught, and 5 omega naught, and 6. I want to find how much of every frequency is found in the signal. I do the same thing. So you get the idea, right? And when it's all frequencies, okay, becomes an integral. So I have to, if you want to find all the frequencies, you take the integral over every single possible frequency available. Okay? Now what you see here, that's essentially this Fourier series equation. That is the equation that we have to solve to find out how much of a certain frequency exists in our signal. Does that make a higher level sense? Okay, so let's go into the math now. So the goal of the Fourier series So the first thing about Fourier series, it's going to work with one set of signals. And that specific set of signals will be only for periodic. So the Fourier series, we're going to look at how it does it for periodic signals. It only applies, and we'll deal with all signals in general later. So Fourier series only applies for a periodic signal. So if you have a periodic signal, you want to break it up into these complex exponentials, this is the way we do it with Fourier series. So what we're aiming to do is we want to express periodic signals Okay, so what are we trying to do? Take a signal, a periodic signal, and express it as a linear combination complex exponential. So these are the complex exponentials that we want to e to the j n omega naught t. This is the letter, the number in front to do the linear combination, okay? And this can be a finite or an infinite set in general, okay? Where n belongs to integral. So we need to find these. This is what we got to find. Right, if you want to make a linear combination, to know how much of each thing is added, you need to have that number in front. Okay? So we need to find that dn. I think that all makes sense, right? It's like the smoothie recipe. How many ounces of banana, how many ounces of orange, how many ounces of milk? So to get that amount of ounces, that's what dn is. Okay? So how do we get dn? Well, if we look back here, this is the basis of that. Take a signal, divide it by all these frequencies, and figure out how much of each of these is coming up. And that equation is, I'm going to put it right here, what we found. Okay? Now, because it's periodic, it's taken over any period, and we average it over one period. Okay, so that's how you get this dn value. And this dn value, this is known as the Fourier series coefficients. And dn are complex valued in general. Okay? And these two together are known as the Fourier series pair. All right, so we want to take a signal, a periodic signal, and we want to express it as a linear combination of complex exponentials. But to do that, we need to find this number in front, this dn. Okay? Again, think of it in the drink analogy. How many ounces of each frequency do we need? Okay? And so, how do we calculate that? With this equation down here, which is pretty easy to see how it comes up from the previous page. Okay? So Fourier series, all you have to do in Fourier series is solve this integral. That's it. That's the extent of our signal theory. Why are we doing it? Because we're breaking up our signals. Okay? To actually calculate it, it's just solving that integral. And that integral is over one period of the signal. And that could be any period anywhere, as long as it's one period. Okay? So let's do some examples. That's Fourier series. That's how we're going to break up a periodic signal with a linear sum of complex exponentials. So let's do a simple example to start with. Okay, so but the important thing here is that Fourier series only exists for periodic signals. So we're just going to look at periodic signals first. And we'll get to every other signal. So we want to find the Fourier series coefficients of dn. So what are we essentially trying to say? How much of each frequency exists in our signal? Okay? So this is a periodic signal, obviously. So the Fourier series coefficient equation which is that, okay? So we're going to stick our signal in there. So what's our period? How do we solve for period? I just gave it away, but right, so omega naught equals 2 pi over T naught. Omega naught here is 2 pi over 3. So T naught equals 3. Okay, so when you see a periodic signal, first thing you need are your periods and frequencies. Right? All right, so dn, so we plug that in there. So I'm going to leave the T naught on the bottom there, just to, we'll get to what the limits are. Whenever I see a sign, I like to use Euler's theorem and break it up into complex exponentials. So that's what I'm going to do here. So I'm going to rearrange the equation a little bit here, and I will end up with now here's what this one is a little bit kind of not obvious right away how to solve this one. Okay, so we're going to do I'm going to the next page and do something, an important discussion here to be able to solve this integral to see what the actual answer is. Okay, notice the integral is in terms of t, but we have this 1 plus n thing in the top. Okay, our equation dn is in terms of n. So that n is going to have an impact here. So I'm going to have to go to the next page, all right? So bear with me, but then we'll go back to that. So we're trying to solve this integral here, okay? So n and m are integers. Okay, we're going to solve this integral over one period. So I'm going to look at the first case. The easiest case of all is if n equals m, what does this integral become? N equals m, this becomes 0 in the exponent, okay? And this, of course, is this. So if we go from 0 to t naught, for example, okay, of dt, this will equal t naught, okay? If we had a 1 over t naught in the front, everyone sees that, right? That's the easiest case, when n equals to m. Now, the ones that aren't as obvious is if n doesn't equal m. So let's say, for example, n equals 3 and m equals 2. In this case, I get e to the j omega naught t 3 minus 2 dt okay, so you have to solve this integral over one period. And just to see it clearly, I'm going to change it to its sine and cos form. Okay, and then I'll break it up. So what is this equal to? What's the integral of a cos over one period? Zero. Right? You should convince yourself. Go home, see it, solve the integral, you see it's zero. Okay, it's up and then down. You're taking the it's positive area, negative area. They add to zero. Okay? What's this equal to? It's equal to zero. So this integral equals zero. So when n doesn't equal m, at least for the case of 3 over 2, it's equal to zero. Okay, let's try different. That's kind of easy to see because it was one period. Let's try this now for n equal to 4, m equal to 2. So we have a 2 up there now. Okay? So if I write this again in terms of cos and sines, I get cos 2 omega naught t dt plus j over a period of sine 2 omega naught t dt. So my question now is, what is this equal to? We are integrating over one period, t naught. This is cos 2 omega naught. So what's the frequency of this new cos? What's its period in relation to t naught? So what about, okay, look at this. What do we have? Cos omega naught, let's say, is what would cos 2 omega naught? 2 omega naught means it's twice the frequency. If it's twice the frequency, it means it's half the period. So that means that within t naught, I actually have 2 full coses. Does everyone see that? Okay, if your frequency is faster, it means your period is shorter, right? You think it's inverse, okay? So it's got 2 full periods within t naught. If I integrate over that, what do I get? Still get 0. That's equal to 0. Same with the cos, equal to 0. Everyone see that? This is a very important point. This is why I do this example. This is an extremely important point. It's fundamental frequencies. Your period is t naught, but within t naught, 2 t naught is 2 periods. 3 t naught would be 3 of them. 4 t naught would be 4, and so on. So within that one period, you're just going to have integer multiples of smaller periods. And when you integrate over that, it will always be 0. Do you see that? Very important. So what are we concluding here? Then when n doesn't equal m, the integral equals 0. Therefore, if n doesn't equal m, the integral is always equal to 0. So if we take this integral here, I'll get rid of that out of there. So there's only one case that that one holds. So let's go back to our example now. So back to our example. We had dn equals 1 over 3 times 1 over 2j over 1 period of e to the j pi by 3 t1 minus n dt minus 1/3 over 1 over 2j t naught e to the j. We had a 2 pi by 3, right? This is what the equation we had just before I went to this discussion. Okay? So how do we solve this? When does that hold? So if n equals to 1, right, that's the case of n equal to m. So this thing would become 1. The integral of that would equal t naught. Okay? If n does not equal 1, integral equals 0. That's based on the discussion on the previous 2 pages. Okay, so if n equals to 1, that integral goes to the integral of 1, becomes t naught. And for this one here, what did I put there? A t, that should be a 1. If n equals minus 1, that exponential becomes 1. The integral becomes t naught. So we have 2 cases. So we have a solution for n equal to 1 and a solution for n equal to minus 1. So for n equal to 1, d of n is equivalent to d now only for 1. So I put the value of 1 there. It equals 1/3 times 1 over 2j. This thing's in front here. Times t naught. And t naught in our case was equal to 3. So that equals 1 over 2j. For n equal to minus 1, dn becomes d minus 1, and that's equal to 1/3. There's a negative in front there, so I should put that, make it like this. T naught is 3 again. So what we found was that for this signal, sine of 2 pi over 3t, there's only 2 Fourier series coefficients, d1 and d minus 1. And they have a value of 1 over 2j and minus 1 over 2j. So therefore, there are only 2 Fs coefficients. d1 equal to 1 over 2j and d minus 1 equal to minus 1 over 2j. So we found 2 coefficients. So we pass this sinusoid through our smoothie operator, whatever, okay? And we're finding that the sine contains 1 over 2j amount of 2 pi over 3t, and so on. This is what it's telling us. So what we're doing now is taking our signal, and we're saying that our signal x of t, which is sine 2 pi by 3t, can be expressed as d1 e to the j, so using the general equation, as a linear combination of complex exponentials. Okay, so we found that it's equal to d1 e to the j omega naught t plus d minus 1 e to the minus j omega naught t, because we only had d1 and d minus 1. They're the only ones that existed. And so if I plug in the numbers, we had 1 over 2j for d1. Our omega naught is 2 pi over 3t. And then minus 1 over 2j e to the minus j 2 pi over 3t. So what did I just find? That I can express my sine as a linear combination of two complex exponentials. Does that look familiar? It's Euler's equation. Euler's equation says take a complex exponential, express it in terms of sine, take a sine, express it into two exponentials. So what we're proving is that Euler's theorem is essentially a Fourier series decomposition of the sine signal. Okay? And I think I did that right from the beginning. Early on, we said that here's an example of taking a signal and breaking it up into simpler signals. Okay? So a sine signal can be broken up into a linear combination of two complex exponentials. So it's telling us that this sine has, these two things make up that signal. Make sense? Let's solve another one and then go on break. Examples help a lot. But again, it's solving the integral. The hardest thing with the integral is you have a case like that where it's specific integer values, but those are easy to deal with. I'm trying to develop the understanding, or make sure you understand the whole thing about periods and fundamental periods and integrating over an entire period and multiples. If you understood that discussion that I did a few pages back, then you're okay. All right, so here's another signal now. We have x of t equals the addition of two sines. So we want to determine if this is periodic. So the first goal is we know that they're both periodic by themselves. And if you recall back a few lectures, 4 lectures or so ago, is that just because two signals are periodic, when we add them, we're not guaranteed that they're periodic. There's certain things we have to check. Okay? So first, let's determine if the sum is periodic. So how do we do that? We have to look at the ratios of their fundamental frequencies. So I'll call this omega naught 1, and I'll call this omega naught 2. So omega naught 1 over omega naught 2, you got to look at the ratio. And it needs to be what? Rational. So it is rational. Sum is periodic. And then we need the overall omega naught. And that is equal to greatest common factor of numerators over the lowest common multiple of denominators. And that happens to be 2 pi over 15. So omega naught overall is 2 pi over 15, which implies T naught is equal to 15 seconds. Okay, now whenever you have pure sinusoids like this, we don't have to go back and do this discussion I did here with break it down into the, try to do this special cases and all that. Once you see pure sinusoids, finding Fourier series coefficients is really easy. You don't even have to do the integral, to be honest, if it's a pure sinusoid. If there was a u of t next to it or something like that, if we had u of t here, then you can't do that. But if it's a pure sinusoid that goes from minus infinity to infinity, okay, all we got to do is express them into use the Euler's form to break it up. So since we already proved in the previous example that Euler's identity essentially creates a Fourier series breakdown, when you see pure sinusoids, break them up using Euler's identity. Okay? So we take our x of t equal to sine 2 pi by 3t. Let me do it on the next page. So I'm going to take my sine, and that becomes 1 over 2j e to the j 2 pi by 3t. Okay, so I'm just re-expressing it in terms of using Euler's identity. Okay, and now here's the part where you can find the coefficients. What are we trying to do? We're trying to find linear combinations, right? But we're trying to relate it back to this. We want our signal to be expressed as linear combination of complex exponentials, which is what it is up here. Okay, so we have the values in front. What we don't have is this exponent, n omega naught. We have 2 pi by 3 and 2 pi by 5. Okay, so let me just pop in omega naught there. Our overall omega naught, dn e to the j n. Overall omega naught was 2 pi by 15t. Remember, that's what we found up here, 2 pi by 15. So I plug it into that general equation of the sine here. So now what we need to do is look at, so this is telling me that I'm trying to express x of t in terms of this. Our x of t is already broken up into complex exponentials. We already have the dn values already calculated from the Euler's identity. What we have to figure out is what n are they? Okay, so if you look carefully, we have e to the j n 2 pi over 15. If I look at this exponent here, and I look at this, what n value do I need to get 2 pi over 5? So what n would I have to put here to end up with 2 pi over 5? What is it? 3, correct? So if this was, there's a negative in front there, so look at the negative. I have to look at the whole thing. So essentially what you're trying to do is get what n value do I need to make these exponents match. So I need so this would be d of, or I would need n to minus 3. So this value here, with the negative in front of it, would be d of minus 3. If I look at this one, what n value do I need for that? To get this, what n value does it, what do I pop into there to get 2 pi over 5? It would be 3. So this would be n equal to 3. So this here is d of 3. What about this one? To get minus 2 pi over 3, what n value do I need to put in here? Minus 5. So this one is d minus 5. And what about this one? That would be n equal to 5. So this one is d of 5. You see what I'm doing there? This is the general form, what we have to get. So these exponents, there's an n value that makes them become what they are there. So what n value do I put in the general equation to get 2 pi by 5? Well, I would have to put 3 there. Yes? No, because the n is on top. It's not on the bottom. So if I make that n there a 5, that becomes a 3 on the bottom. Is that what you're asking? It can't be 1 over. If it was 1 over, then the 5 would go underneath, and it would become 5 times 15. So that 5 and the 15 cancel, and that becomes a 3. So it becomes pi by 3. Oh, sorry. There's a 2 pi there. I erased the 2 pi, didn't I? That should be there. That was our omega naught. So how do we, what n value do we use to get this? So if you have j 2 pi over 3t, n 2 pi over 15t, what n do I need for these to equal the same? N would equal 3. If I have minus j 2 pi over 5t to be equal to n 2 pi over 15t, what n do I need? I need n equal to, sorry, this one's 5, and this one's 3. Does that make sense or not? You still seem confused. Do you understand this, what we're trying to do? This is the general case here, right? And that's our omega naught. So I need, these things are already broken up into complex exponentials. So I need to know which frequency each of those complex exponentials is. So when I look at this one over here, okay, it's e to the minus j 2 pi over 5t. How does that relate to the general case of e to the j n 2 pi over 15t? I need to know what n value I would need to put to get e to the minus j 2 pi over 5t. So if I want e to the j 2 pi over 5t to equal this general case, what n value do I have to pop in? I would have to put in 3. If I put 3 in, so that means that I used the n value of 3 to get this exponent. So the dn in front is equal to d3. But in this case it's a negative, so it would be d minus 3. Right? There's a negative exponent there. Does that make sense? So what I'm getting is you don't have to solve the integral when you see pure sinusoids. If you see pure sinusoids, break them up into complex exponential form, and then you'll be able to relate it to that general term. Tell you what, let's take a break and we'll do one more example to see how that's done, okay?